Good day to everyone, and thank you for taking time out of your schedule to join me today to learn a little bit more about how to choose the right distribution when working in at risk. My name is Michelle Jackson, and I am the product manager here at Palisade Corporation. So for those that may not be familiar with Palisade, we are a global company with our headquarters based in Ithaca, New York. But we do have offices around the globe. And I'm putting up this contact information for you to be able to reach out to us at any given time. And I, of course, would recommend reaching out to the regional sales manager who sent the invite to this webinar to you. However, if you've stumbled upon this just by visiting our website, you may not know who your regional sales manager is yet. So feel free to utilize any of these contact phone numbers and emails to reach out to us. And we are here. We offer trainings and seminars and all sorts of conferences around the globe that give you an opportunity to not only learn from us, but have the opportunity to ask questions and to get some feedback on what you're doing. So I could go into a long diatribe about how we were founded back in 1984, and we have so many thousands of users and a lot of Fortune 500 companies use us. However, we'll skip those slides and just say we're here to talk about at risk. And we're here to talk about this flagship product of ours and how to utilize one particular segment of it. So I will do a very, 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 very brief overview of what at-risk is, but today's webinar is really truly about choosing the distribution or finding a way to represent your uncertainty. So of course, you are probably well aware that at-risk is the leading risk and decision analysis add-in for Excel. And it utilizes a technique known as Monte Carlo simulation in your spreadsheet models. So by using simulation, at-risk tells you not just what could happen, but quantifies how likely something is to happen. Essentially, at-risk answers questions such as, what are the chances we'll make money on this venture? What is the probability we'll finish on time or within budget? What is the range of capital reserves necessary to meet our goals? These are questions that a lot of us these are types of questions that a lot of us have to deal with in our day-to-day businesses or whatever industry or applications we're in. However, a key component to Monte Carlo simulation is assigning a proper distribution for at-risk to draw from when conducting the simulation. So today, we're not going to get heavily into finding out what the chances are, what the probabilities are, what the range is. We're not going to go into the analysis of it all. We're really going to talk about the inputs. But just to give you an idea, essentially, our goal is that we're hoping by the end of the webinar, you'll feel more comfortable with the process of choosing distributions or representing your uncertainty with distributions. So in your Excel and at-risk models. So how are we going to do this? We're going to do a very quick overview of Monte Carlo simulation and the steps involved in setting up a model in at-risk. We're going to basically suggest some questions to ask yourself when you are choosing a distribution, such as, do you have data? Can it be used? What do we know about the input? Those kind of questions. We'll also cover some distribution fitting. So if you have pre-existing data, we're going to show you how at-risk can fit a distribution to your data. We'll also take a look at a few examples. So we're going to cover a lot of different inputs, and I promise you we will get into at-risk, but bear with me when I am going through a couple of things that you're not seeing at risk, because it's going to be just talking about those input distributions. But we will get to some model examples of it. And then we'll also just touch base on additional things that you may want to cover. And this quote pretty much says it all, right? There are known knowns. These are things we know that we know. There are known unknowns. That is to say, there are things that we know we don't know. But there are also unknown unknowns. There are things we don't know we don't know. And it takes a little while to kind of absorb that, right? And that is a quote from Donald Rumsfeld, and he was the defense secretary for the United States back in 1975 to 1977 and 2001 to 2006. But when I saw this quote, I was like, wow, this is essentially what we talk about when we talk about our models, right? The known knowns are known inputs, are known factors. We know what's going to happen. the known unknowns, are what this webinar is about. It's about, we know that we don't know all the details about our input. We know that we don't know those details. So how can we represent it in our model so that we can analyze our model? So that's what, so the text that I highlighted in white in this PowerPoint slide is what we're covering today. Then also know that there are unknown unknowns, and those are things that we can't represent in our model. So what I'm saying, why I include that is the fact that a lot of times there's a misconception, like, you know, if we run a model, we'll know exactly what to expect. The reality is you won't know exactly what to expect, but you will have an idea of the range or the probability or the chances of getting whatever it is that you're looking to achieve. So just focus on that white sentence there. There are known unknowns. That is to say, there are things we know we don't know. So how are we going to represent them in at risk? So let's do a quick recap of the basic steps that we do. And if you've watched any of my previous webinars, you'll already know that I go through these 6 steps in every single webinar I do, because I think it's so important to iterate that there is a process when you're doing this modeling. And the first step is exploring model logic, basically getting your ideas on paper. What are all the different knowns? What are all the different unknowns that are the known unknowns? Like, let's get those on paper, or in our spreadsheet, I should say. I always say on paper, but it's not really on paper. But exploring that model logic, finding out what it is that we're looking to achieve. We're going to designate those inputs, and by that we're going to then assign distributions or fit distributions to pre-existing data that will be represented in our model. So that is going to be our known unknowns. We're going to assign a distribution there. We're also going to designate our outputs. Let at-risk know which outputs we are most interested in. Is it net present value? Is it completion date? Is it total cost? Is it revenue? What is it? So we're going to designate those outputs. Then we're going to simulate. The simulation step of this is the easiest portion of it, because at-risk does all the work for you at that point. You're going to simply let it know how many simulations and how many iterations for those simulations. Then we're going to analyze results, and that's when you, as someone that is setting up, you know, whether it's your risk manager or your cost estimator or your project manager, that's when you're going to look and go, okay, this is the story that this model tells us. This is what could happen, and these are the chances and the likelihood that this is going to happen. So now, after you do that, you then have to find a way to communicate those results to others, and that's also part of the process. So let's go into at-risk for a quick second. So when we are in at-risk, you're going to see a ribbon at the top of your Excel here, so where the Excel ribbon normally is. And note that the Excel ribbon is still there. We still have our home, our insert, our page layout. We are still in the same environment that we've always been in. However, we also have this at-risk ribbon. Today, this is where we're going to focus our attention here. We're also going to do a little bit here, and we're also going to do a little bit here. This is where we're going to focus the majority of our attention today. And to start off, I'm just going to quickly show you, and I apologize for those that have been in other webinars with us that we're going to do this, but I'm just going to quickly show you a basic at-risk example, and if you've been in other webinars, you've already seen this. Let's go ahead and take a look here at this is a very basic profit equals revenue minus cost, right? It's a model that we have. We have already assigned or defined our input distributions, and I will show you how to do that, but I want to run a simulation just so that for those that are new, basically we would say model logic is profit equals revenue minus cost. That's step 1. Step 2 is defining our inputs. We have defined our inputs using our defined distributions, and for these particular examples we've used just the normal distribution, primarily because that's what a lot of people, when they're new, they know about the normal distribution because they took Introduction to Stats back in college or even in high school. Most people are familiar with that. So we've assigned our inputs already, and then it's like a cooking show, right? And then we click here and we go to our output. We've already defined our output by clicking on this Add Output. We've said that our output that we're most interested in learning about is profit. So here we have that. Now, if we run our simulation, let's say let's do 100,000 iterations just because I can talk while it runs. And I'm going to go ahead and start the simulation here. So we're going to watch that run. Now you're going to see the numbers changing in cells C3 and C4 and C7. So what is happening? Basically, during every single iteration of the simulation, at-risk is randomly selecting a value under those normal distributions that were assigned in cells C3 and C4. After it randomly draws individual values, it puts it into our example spreadsheet and then recalculates profit for all 100,000 iterations that we have going on here. So what this does is all of those profit results are then put into their own histogram, and it creates its own distribution. So you can see here now all of a sudden we have this distribution that is completely settled out, right? So even after just 10,000 iterations, it's completely settled out. Now, I have this running in what's called demo mode, and the reason why it's running in demo mode is so that I can talk longer and explain to you what happens during Monte Carlo simulation, but it's also cool to see that the numbers updating each time. Now, obviously, this is running a little bit slow for my liking. If I wanted to run faster, I can stop the updating of the Excel worksheet here, and I can stop the updating of the output here, and you'll see it will happen much faster. So all of a sudden now it's chugging through, and it will give us a final result when it's all done, which is great. But imagine trying to recalculate this 100,000 times, and it takes us no time at all to do that. So this is an example of what a distribution would look like after running the simulation 100,000 times. And the way we had step 1, model logic, step 2, assigning input, step 3, assigning output, step 4. We run the simulation. Step 5 is analyzing results. So we can look here and say 6.9% of the time we're not going to make a profit on this deal. 6% of the time will exceed 40,000. We can then drag this over and say there's a 44% chance that we will make between $20,000 and $40,000. So we're talking chances, probabilities, ranges, so that is what at-risk allows us to do. It tells a bigger story. Yes, we can add correlation to this. We can do all sorts of other things to it. But then it's also a matter of communicating these results. So you could say, one out of, every other time you're basically going to exceed $20,000. However, there is a 6% chance that you will be less than, you'll lose money. So this allows us to tell a different story. So those are those simple steps without any effort. But let's go back to the same model and let's talk about some of the inputs that we could use here. And what I want to do first is, instead of just having revenue, let's go ahead and insert a couple rows here and a couple rows here. And we're going to do something a little different here. We're going to say number sold, and we're going to say unit price, and then we're going to say here, we'll say base cost, and here we'll say unit cost and total cost. And say here we decide, so we're just going to put single point estimates in there, and this brings up a great point, like how many times people end up using single point estimates, right, when they're guessing at how they're going to proceed, and they'll say, yeah, well, we think we're going to sell about 500 of them. The unit price is probably going to be I don't know, $200. Let's call it $200 here. Let's go ahead and add a dollar sign to that. So we're going to say it's going to be about $200. I don't need the decimals. The revenue equals this times this. And the base cost, we think it's going to be about $40,000. And the unit cost, we're going to guess that the unit cost is about $80. And the total cost equals this plus this times this. Okay, so we can look quickly at this, and let me just, because of who I am, we don't want that bold, so there we go. We can do that one bold. Okay, so if we look at this, we can see here that it's very, it still has that same information that we had, right? We have revenue and we have total cost. So I've just kind of input a couple extra variables in there so we can talk about some of those distributions that we're so curious about, right? So now we're going to just kind of start from ground zero, essentially, right? Because we're at this point of, okay, this is what we think it should look like. And the profit is still C5 minus C8. Okay, it's still revenue minus cost, but we have these additional input variables. So let's talk about some of the things we have to think about when we go, okay, we need to add a distribution to this. If I go into define distributions and I click on my all tab and I look at this, this might give you some anxiety going, oh my word, I do not know where to begin, right? My suggestion to you is don't even click on the All tab, okay? Do yourself a favor and at least narrow it down to whether it's a continuous function or a discrete function first. And then we're going to give you some other questions for you to answer. I'm going to show you those in a PowerPoint slide. But the biggest suggestion I have for you is click on the Common tab. I forget what the actual statistic is, and obviously there's no way to really know exactly how the percentage is, but we're going to assume as a company that 95% of our users use these distributions more so than any of the other ones. The other ones are very specific, and they're specific in what industry they're in, what application they're being used for. So do yourself a favor and just focus on these until you have a reason not to. Okay, so let's go ahead and take a look at, is there a correct distribution? Let's just start with that so that we don't have that anxiety. Well, is it theoretically correct? Does it conform with your industry standards? Is it data-driven? These are all questions that we can ask ourselves, okay, about our thing. Is it pragmatic? In other words, is it intuitive to others that you are communicating with? And does it make sense? Simple question, like, does it make sense to have this? So that's when you're going to think of whether or not the distribution is bounded or unbounded. So ideally, to find a quote-unquote correct distribution, it would be a combination of all of these, and at risk will provide you the capability of fitting your data. However, if you need to communicate that information to someone that doesn't understand data fitting, if you tell them they used a Pearson-6 distribution, they may focus and digress and ask you why you would use a Pearson-6 distribution instead of an industry standard. So all of a sudden, there is going to be no perfect distribution, okay? There will be accepted distributions. There'll be very, very close to accurate distributions, but there are no perfect distributions for any situation. However, today is going to give you just ideas of when you can use certain things. So here are some questions to find out if you can use your data. Is your data representative of the population? So if your data are representative of the population as a whole to your problem, you can most certainly use it. And we'll show you how you may want to fit your data to a distribution that can be used in your model. Do you know the true minimum and maximum to your data? This is an area that is so important to take a more focused look at. Because if your data does not include the true range, like the true range of the outcomes, then a significant event or outlier could potentially be overlooked. Case in point, I am sitting in my home office. Why? Because the roads were closed. That is something that we may not have put in our prediction as to whether or not Michelle would go into the office today. However, this very rare situation where we're getting 18 to 24 to 30 inches of snow, depending on where you are in this area, that is that outlier. So that true range of going, would we expect to get this in March? So that's what I'm talking about. Do you know your true bounds? So unfortunately, phrases like minimum and maximum most likely can actually be misleading or have unforeseen implications, because if you were to say the maximum, the maximum number of inches of snow we think we would ever get in March would be 12 inches, and all of a sudden we get 36 inches. Well, we haven't taken that into account, which means we haven't taken into account that our county would close our roads, right? So when choosing whether or not you should use your data, you may also want to think about what source is the data coming from. Is the data from experiments and observations that were well monitored? Were the observations subjective? Were they measurable? Were the data from surveys? Did those surveys have specific options, or was it free-form? Did your data come from a computer database, or maybe it came from other simulations? All of these questions may affect your decision on whether you want to use your actual data and to what extent. These are just some of these thought processes that we have to go through. So what do we know about the input that you're trying to represent with a distribution? So we had whether or not we could use our actual data. Now we're going to talk about what kind of distribution, like what are the factors that we want to think about. So again, before we dive into at risk, these are a list of input attributes that are important to consider when you're trying to figure out a way to represent those known unknowns. One of which is it continuous or discrete? And we're going to, just so you know, I'm going to list them off, but then we're going to go in and we're going to talk about each one of these in greater detail. Is it continuous or discrete? Is it symmetric or asymmetric? Is it bounded or unbounded? Is it parametric or non-parametric? Is it univariate or multivariate? Is it based on additive or multiplicative process? Which one is it? So these all have this impact, okay? So the continuous versus discrete. As you saw in here, let's go to this one. There are two types of distributions. There are discrete and continuous. And when we look in our define distributions dialog, we do have a discrete distribution tab and we do have a continuous distribution tab. So these are the two different kinds. If a variable can take on any value between two specified values, it is called a continuous variable. Now, those two specified values could be negative infinity and positive infinity. In fact, the normal distribution that everyone knows so much about is actually on the range of negative infinity to positive infinity. So if it can take on any value in between, it's a continuous distribution that you'll want to use. If we're going to use a discrete distribution, the variable has a limited predefined number of possible values and leaves very little room for subjectivity. So this is a situation like when you get like a survey. You have choice A, choice B, choice C, or choice D. That's it. You don't have B and a half. You don't have C and a half. You have choice A, choice B, choice C, choice D. So this is where a discrete distribution would be. So when evaluating your variable, you can be, when evaluating whether or not your variable can be represented by a discrete distribution, discrete distributions take one of a set of identifiable variables, each of which has a calculated probability of occurrence. So think of probabilities of flipping a coin, selecting a card from a deck, rolling dice, number of cars, etc. Okay, the outcome of flipping a coin would be represented by a Bernoulli, or a binomial with an n set to 1. Poker hands will use geometric. Frequency of arrivals in a queue would be Poisson. Okay, so these are all different things. So the Poisson distribution here, this one, if I open this up, represents the number of random arrivals during a set interval of time or distance. So it has one parameter that has to be positive, and it assumes independent events with a constant rate of occurrence. That shows you a little bit more about discrete, and you can see some of the discrete ones that I've put here: binomial, geometric, negative binomial, discrete uniform, which is different than uniform. Discrete uniform is going to be your A, your B, your C, your D of a particular survey or what have you, or rating on a numbers 1 through 5. You know, it has to be either 1, 2, 3, 4, or 5. You have to color in the little circle, what have you. A continuous variable is going to be, so let's open up that defined distributions thing again, go to our continuous variable thing. A continuous variable takes on an infinite number of values within that predefined range. So in other words, the majority of the time we can only measure them to some degree of precision limited by our instrumentation. But they can have any value. So for example, asking someone to weigh themselves, the temperature, the speed of something. These are all situations where the instrument doing the measuring determines how precise the measurement is. Examples include, you know, stock price returns, log normal, allocation of wealth, Pareto. So you can see this allocation of wealth. Triangular is a situation where you just have to know that the minimum max, nothing exceeds or is below that minimum, so, or max. So nothing exceeds the maximum, nothing is below the minimum, and you have to be certain of that. PERT distribution, same thing. However, there are ways around that uncertainty in at risk, and we would use what's called alt parameters, and that's a whole nother level, and we might get into them if we have time today. So some other questions that we may ask ourselves is going to be whether or not it's asymmetric or symmetric. So we can look at this and see which ones are symmetric and which ones are asymmetric, right? We can see the beta distribution, we can see the normal distribution, the triangular distribution, uniform distribution. Those are all symmetric. However, note that you can force a symmetric distribution to become asymmetric by changing its parameters a lot of times. So just note that that's possible. A uniform distribution you can't, but on some of the other ones you can. However, if we look at the other ones, we can see the Pareto distribution here. This is asymmetric. Log normal is asymmetric. So just know that there are possibilities. Something else we can think about is bounded or unbounded. Bounded and unbounded refers to those extremes of a distribution. A bounded distribution means that all values sampled will be between two specified values. So let's take a look at that uniform distribution. If we look at this, we are going to say that 100% of our values drawn will be drawn between -10 and 10. It will not have an 11. It will not have a -11. All of the values will be drawn between these two bounded ends. And this is where you really do need to take caution that when you're thinking about your input variable or your known unknown, you want to think about the fact that is it possible that all of a sudden it would just whoop, drop off that rapidly? Again, it has to be, it ends at 10, it can't be anything more. It won't be 10.1, it won't be 10.0000001. It drops off at 10. If you can confidently say, yes, the maximum is 10, period. Then you can go ahead and use a distribution that is bounded and has that very significant chop off. Now, if we were to look at our normal distribution, if we look at our normal distribution, you're going to see here that it's unbounded. It goes on to infinity, okay? Infinity and negative infinity, okay? So you're going to see here that even though it'll say, if I go here, if I drag this over, when I drag this to the left, you're going to see that this top marker is going to change to infinity. See how it changes to negative infinity and positive infinity. So this is showing you that this is an unbounded distribution. Okay, now when we think of, and I did put together a quick little thing to give you an idea. Bounded, these are some of the bounded. The blues are our continuous, the reds are our discrete distribution. Unbounded and partially bounded, meaning it's bounded on one end. It might be an input distribution where it's bounded by 0, so it's only bounded on one end but can go on to positive infinity. That would be called partially bounded. So these are ideas when you're asking yourself about these known unknowns. These are the things that you would ask yourself. Unbounded, note that there are no red ones here. Why is that? The reason why is because if it's a discrete distribution, it needs to have that predefined values set to them. So you can't have it be unbounded because there's no way to get all of those values out on those tails of negative infinity and positive infinity if it's a discrete function. Okay, so that's what that means. As far as parametric and non-parametric, these are basically parametric distributions are determined by mathematics describing a conceptual probability model. So the parameters will include things such as mu or sigma, the small sigma for standard deviation, gamma, lambda. It's going to speak Greek essentially. When would you use a parametric distribution? You would use a parametric distribution when theory supports the distribution. When the distribution has a proven accuracy for modeling your specific variable. When the distribution matches the observed data well, which is a lot of times you'll end up with parametric when you go ahead and do a fitting distribution, right? Because it'll match your data well. When you need a tail that extends beyond your observed minimum and max, you're going to use a parametric one. So, example, the normal family distributions, again, all have the same shape and are parameterized by the mean and standard deviation, or mu and sigma. So that means if you know the mean and standard deviation and that distribution is normal, then you know the probability of any future observation. That goes back to the central limit theorem and everything that we learned in Introduction to Stats, where 68% of your values will land between +1 and -1 standard deviations away from the mean. So that is going to be a parametric distribution. So all of these speak Greek. Non-parametric equations, and let me just show you some just to really give you an idea here. So if we look here, where's my normal? There it is, alphabetical order, Michelle. So if we look here on the left-hand side, you're going to see the parameter mu and the small sigma. Okay, and you can see that when I mouse over, it's going to let us know what that parameter is. It says, is the entered standard deviation of the distribution and must be greater than or equal to 0. So it's going to let us know what it's looking for in there anyway. Now, if we look at, say, the PERT distribution, let's go back in here, click PERT. Now, all of a sudden, it's speaking English, right? Minimum, most likely, max. This is a non-parametric distribution. These are empirical distributions for which the mathematics is defined by the shape required, such as triangular distribution, or in this case, PERT distribution. And our arguments will typically be subjective in nature and include like minimum, most likely, max, like it does here. So envision sitting around a boardroom and you ask people, what's your worst case scenario? What do you think is going to be the absolute minimum? What do you think is going to be the absolute maximum? And then coming to a common ground and putting those values in there. And you can actually, this is crazy and we won't get into it today, but you could actually do a distribution of even all of the people in the board members' minimums and make that a parameter in your per or your triangular distribution. So you can actually embed, distribution functions inside other distribution functions. Not something we'll get into today, but when would you use non-parametric distributions? Essentially when theory is not prevalent, when there's no commonly used models to represent what you're doing, when the data itself is very limited so you can't really fit a good curve to it or what have you, or distribution to it, when knowledge about the situation is limited to just general beliefs and just a little bit of evidence. That's when you want to use a non-parametric equation. Distribution. So univariate and multivariate is the other one that was on that list. Univariate describes a single parameter or variable that is not probabilistically linked to any other parameter. And multivariate means there is a link. So that's when you start thinking about correlation. So to make it easy for some of our users, I put together a quick, and it doesn't include all of the distributions, but it at least gives you, so this right here is just almost like a decision tree of the different inputs and basically the different attributes that I just walked through with you. So is the data discrete or continuous? It's discrete. Okay, then can you estimate the outcomes of the probabilities? Yes. So it'll go through, and then at the end, at the bottom here, I've put a suggested distribution that you could use that at-risk has. Okay, so does this include all of them? No. Is it a great starting point? Absolutely. And that's what we want to provide for you, is a great starting point, because then over time you will become more comfortable with the whole concept of using distributions. And once you're comfortable with that whole concept of using distributions, then you will be able to better understand which distributions fit your situation better. And I can't take credit for this flowchart. This flowchart was actually derived from this strategic risk-taking book. It's a framework for risk management. And so just know that this will also be included, that you can also walk through some of the other stuff. Now for the ones that are intermediate users or even some of the new users, I'm going to show you a few different things with that introduction model that I already started. So I'm going to go ahead and close up this one. So let's go back to this one here, and let's start adding some distributions. Okay, let's try to have some fun with this, right? So let's say we don't really know what's going on, so we're just going to add a triangular distribution for units sold. Okay, so let's go to at-risk, and I am going to just unload this add-in because I don't need that right now. So in order to define a distribution in at-risk, if you're new to at-risk, you just simply double-click on Define Distributions, and let's go ahead and choose Triangular Distribution. For this particular one, let's say that it's the minimum sold will be, let's say the minimum sold will be 250. The most likely is 500, and the max is 600. This is what we expect to sell. Maybe we already have 250 pre-ordered and we haven't even gone to production yet, but they ordered it online, they ordered it ahead of time, so we already know. We think it's going to be 500, but the reality is our distributor cannot produce more than 600 of what we have. It's just physically not possible. Okay, so these are kind of those things that you're going to ask yourself, but we are anticipating that this is going to be a hot item, so we're going to expect about 500 to be sold. So maybe this is the distribution we go ahead and use. Along the same lines, we could do the same thing for unit price. So let's go here and say define distributions for unit price. If we, again, maybe we use triangular, again, we could use per is another one, and I'll show you a comparison of per and triangular in just a bit here. But maybe for this one, we say the minimum is actually 120 because there's probably going to be someone out there trying to sell a fire sale on it, but this is what we think it'll actually look like. And you see I'm using static value. What does static value mean? Why do we have a static value? Why is that a parameter in this distribution function? The reason why we have a static value is so that when I click OK, the value that shows here is not going to distract others. What I mean by that is, so if I click on this one here, if I were to cut that out, it's going to show this. Even though our most likely is 500, and that's what people typically, when they look at their spreadsheets, they think most likely, average, the mean, whatever it is, whatever statistic they use on a regular basis, that's the number they want to see in that cell. But it's important to realize that when you are working in at risk, this number is just the door. It's what's in the room or what's in the cell behind the scenes that drives your model, and that's this right here. So what we want people to do is we want people to feel comfortable with what they're used to seeing. So they're used to seeing the 500 there. They're not used to seeing the average, which is going to give you that 450, right? So if I click, or the expected value, which is going to give you that 450. Here, we have 500. So now we've specified that we want the most likely to be represented there. Okay, so that's what that risk static is. Now, I am going to also do base case. Base case, maybe this is a parametric situation, and we know that the base case of this certain production, base cost of this certain production is always 40,000 with 3,000 standard deviation, and we're going to just do a normal curve on that because that's what has happened in the past. It's kind of like the industry standard, or we could even use 4,000 as standard deviation. So let's go ahead and click OK on that. Unit cost. Maybe unit cost, let's say for unit cost we do, I'm doing different ones primarily to show you that you don't have to have all of the same distribution in an example file. So let's maybe do a PERT distribution. I used a triangular distribution. I used a normal distribution. What is a PERT distribution? You know, there's probably people out there that haven't heard of PERT, right? In this situation, we could say the minimum here, just like a triangular distribution, the minimum here might be 75, most likely is 80, max is 100, and the static value we're going to leave at 80. So this right here has a shape similar to a normal curve in the sense that things are more gathered closer around the mean, or the most likely, I should say, around the most likely, and not as heavy on the tails. Versus if we were to overlay, and I can overlay by clicking this button down here, if I overlay a triangular distribution on this, you will see that if I were to overlay a triangular distribution on this, it still uses the same minimum, most likely, and max, correct? However, if we look at where the simulation is going to draw the different iteration values, the blue will be more around the most likely if we use the PERT distribution. So it'll be centered, the unit cost will stay more consistent around that expected $80 versus if I were to use the triangular distribution, it's going to have values that are more in this worst case scenario. So if we were bringing this to our board and saying, hey, do we want to roll forward with this? We would have to really be cautious because if we put in the triangular distribution, it may show a grimmer, if that's a word, a more grim, I don't know, a worse picture because it's going to make the unit cost look like it's always, you know, there's a good chance that it's going to be, the unit cost is going to be $90 or $95, and if we're selling it for $120, we're not making a lot off of that. Okay, so just to keep in mind that, so that's a good example of the difference between PERT and triangular. Okay, So let's go ahead and include PERT just because we can, essentially. Okay. Now, to add an output here, we just simply click on Add Output. We're going to name this profit. So here we have our unit sold, unit price, base cost, unit cost. Now, when I look at unit number sold, you might have recalled when I described the discrete distribution, I said number of cars, number of people in a queue. The word number of could make you think that this would be a discrete distribution because of the fact that when I describe discrete distribution, I use that number of factor. Here we have number sold. Granted, we want it to come out as an integer value. We don't want it to be for 452 and a half products. You can't sell 452 and a half products. So what we can do is we can actually wrap this with an integer function around it. So let's go here and here. So now when we put on our dice icon up here, and this is part of at risk, just being able to show you what happens behind the scenes. If I turn my dice icon up here and I click on my F9 key, it's going to show you how it updates. Okay, so you'll see that it's an integer value for number sold, even though it is a continuous distribution. It is taken on any value between 250 and 600. However, it's not doing halves or anything like that. And the difference is it's different than number of people in a queue because there may be a 10% probability that you'll have one person in the queue and 20% probability that you'll have 4 people in the queue. However, you're not going to do that for every value between 250 and 600. So that is where the continuous comes into play, and it's not going to be about the instrumentation measuring it. It's just a simple fact that it is continuous because it's spanning over such a large range, so there aren't just individual predefined values that will be there. So number sold and unit price. This may be a situation where the unit price, and this is important to cover too, even though I was going to get into correlations, I think it's important for those that are new to know that it's essential that you take correlation into account. And if you're not familiar with correlation, again, take a look at that on-demand webinar about correlation. But essentially what this is this is going to allow us to say, hey, when we're sampling, let's make sure that when the unit sold when the unit price is low, that the unit sold is high. Let's make sure logistically it makes sense. And we don't want it to have a high unit price and, and have a really high number sold because that goes against that logic, right? However, there are certainly some situations where it will come into play, right? But it is not the standard logic. So if we wanted to define these distributions, and I'll do it really quickly, say we said that there's a 0.7% correlation between these two variables, and by that I mean if we look at the unit price along the x-axis here, I'm sorry, we want negative. That's why it's not making sense to me when I look at this. If we look at unit price along the x-axis, so in this window here, if we look at unit price here as being on the x-axis, as unit price increases, the amount sold decreases. Unit price increases, the amount sold decreases. Okay, and this is showing like what it may look like between these two variables. That's how we want it to sample out. If we wanted to have a stronger correlation, you just drag this over this way. If we think it's really tight, but like I said, there might be a situation where it's in demand, so some people are willing to pay more. That might be a situation where it'll stray from that pattern of being tightly correlated. So let's go ahead and click OK here. We'll select a location for our matrix. We'll put that here. Click OK. So you can see here that now when I click on this not only do we have an integer function, we also have a correlation matrix function embedded inside the risk triangular function. So you can see that all of the functions that at-risk does are all tightly tied together to what happens in Excel. So let's go ahead and turn off our dice icon so we can see the values that are easier on the eyes, right? Because it's about communicate. That step 6 is going to be important when you bring this to your board or what have you afterwards. We want to have that step 6 of easy on the eyes, what people are used to seeing. That'll help tell the story. Now, let's go ahead and also take a look at the fact that we can add multiple outputs. So let's also take a look at what revenue and total cost will look like at the same time. So we'll change those to outputs as well. So we have inputs, and even though these revenue and total costs are inputs technically to this profit, we can actually let at-risk know, like, hey, we're curious, want to take a look at that after the simulation. Now for the simulation, I'm only going to do 10,000 iterations. I'm going to click start, and while I do that, I'm going to quickly check. So I'm going to stop this so we can see it. So I'm going to show you a fun function. This function's really neat. So here we have our output of profit. And for those that know about sensitivity analysis, we can now look at this tornado graph and see that unit price is the biggest driver out of our inputs for this output. So this gives us an idea of which inputs have the most impact on our outputs just by looking at this quick tornado graph. However, what if we wanted to look at just revenue and cost? If we want to look at just revenue and cost and we don't necessarily want to break it apart into these other little things and we just want to say, hey, do I need to talk to my manager that's in charge of pricing and marketing and social media presence, etc., or do I need to talk to manufacturing? Like, which department do I need to really look into? Well, let's go to this function that is called make input, risk make input. So I'm going to actually delete the output range on this because we don't need to see that output range here, but I just wanted to show you that you can have those outputs as well. So now you can still see this is just a regular cell adding it up, and then this still relates to that, but I've removed that output. You can have it in there, but just to avoid some confusion, because I want to actually put in this. I'm going to say equals risk make input here. And we're going to do the same here. Risk make input. Actually, instead of typing it in, I want to show you where you can find it. I tend to type my functions in, but if you want to make this a risk make input, select here, go to insert function, go to miscellaneous, risk make input right there. Okay, it'll say, do you want that cell? Yes, that's the cell that I want. Okay, it'll make that risk make input without you having to type it in and add parentheses. So now all of a sudden it looks like we have 6 inputs, right? However, if I run that simulation and look at that same tornado graph, it now will only have revenue and total cost. Because what we have done is we have told at-risk, hey, I don't want you to report on all of the inputs. I want you to make this an input, okay? And you can just have it just focus on the 2 instead of the other sub input, shall we say. Okay, so let's turn off the updating there. So I hope that is one that a lot of people aren't necessarily familiar with. Another example of the same risk input is going to be in our example file. Let's actually close out of this example file and go here, example files, and it is event risk. There we go. Okay, so I'm going to open up this one. And you can see, you just saw the way to navigate through that example files list. Just look for what you're looking like. Do a quick search, and a lot of times it'll just pop up. and bring up the model that you're looking for. So this is a situation here where if we look at this particular cell, and I'm going to zoom in here, this right here is an example of how this particular function will help with tornado graphs, in particular when there are two input distributions for each input. So this typically can be seen a lot of times in risk registers, or in this situation where this is like a risk register, this is like a large risk register in and of itself. The fact that there is an event, there's the probability of it occurring. We want to simulate whether or not it occurs or not, and we do so by representing that occurrence with what's called a Bernoulli distribution. So if I look here, this is given a 1%. You can see the little tiny 1% here. That'll turn on to be a 1. Otherwise, it will always be a 0 here. So if I actually hit my F9 key 100 times, 1 out of 100 times on average, it would come up with a 1. And if so, the impact will be $500,000. So this particular, let's go equals this times this. So this particular cell here is going to be, it'll multiply out 0 times 500,000. If there's a 1 here, it'll put a 500,000 because it'll be 1 times 500,000. And if we copy this all the way down here, we will see that. So I am actually going to run a simulation on this. So I've removed the risk make inputs for now. But if I even turn this on a dice icon here, and I can click my F9 key, you will see that as I click my F9 key, occasionally you'll see 1 show up, and it'll give us the total actual impact. So this is like one big, large risk register that is talking about, events that most certainly shouldn't happen, but could happen. Confidential data loss, large customer goes bankrupt, failure of a new product launch, and the impacts, the financial impacts. So if you're a cost estimator or a risk manager, this is a fantastic file for you to see. Now, if I run a simulation on this, we're going to see, we'll take a look at that tornado graph. So of course, as expected, the 0 is going to be super high, right? That's because that would be situations where all of those occurrences were 0. Now, if we look at the tornado graph, I can look here and I can see entry of new competitor as the first one here occurs. Entry of new competitor impact if occurs. So this is actually taking each one of these inputs and putting it, so it's taking this as an input, it's taking this as an input, this is an input, this is an input, and putting it in a tornado graph. That is not what we want to see, because this isn't, we want major failure of IT system to be one complete input. So how do we do that? We do that with that risk make input function. So if we go here, let's turn off the dice so it's not confusing to people. Go insert function, go miscellaneous, risk make input. We'll say that is okay, and then because we're in Excel, we can drop it down. Now I've added risk make input functions for all of those. We can run our simulation again, and now it'll have just the actual events, not, so see, now it just has the actual impact. So now we can see, yes, entry of new competitor definitely is the one that has the most impact. Failure of new product on launch, that's another one. But fraud, we don't need to worry about it so much. These are the ones that we need to worry about. Problem with manufacturing process could have a little impact, but these are the ones we need to worry about. So that's just another example of a great input distribution function that will also help you as you navigate through at risk. I definitely have to hit on distribution fitting. So let's go ahead and take a look at that. So we're going to go to distribution fitting here. So when working with distribution fitting, again, it is important to assess the quality of your data and where it comes from. So if we open up this example, let's delete this. Note that whenever you open up any example files in at risk, there will typically be an explanation on that first page, and then on the second page it will be some sort of the data or your model itself, and then a lot of times we put up static images of what your results may end up looking like. So for this particular example, the data in this column C is 3 years of weekly demands for a company. And we want to fit this. So if we took a look and just went to Data Viewer here, just know that you can go to Data Viewer, we can click OK. It will actually, we can drag this out so we can see it. It will actually graph out our data. Okay, so that's what this column C of data looks like if we were to create a histogram out of those values. Okay, so what we're looking for is we're looking for a curve that will best describe this particular distribution or this particular variable. So we're going to do the fit distribution on this. So we're going to distribution fitting, click fit. We'll do a new one and we'll say webinar. And then we're going to click on distributions to fit. This is where, again, we're going to start thinking about, is it a fixed bound? Is it bounded but unknown? Is it open? Does it extend to infinity? These are questions that we already asked before, right? So again, it's all coming into play here. So for this one, we can say we know it's a fixed bound of 0 because demand can't be less than 0. It can only be positive. So you'll notice when I toggle between these two, the list of possible distributions that it will even try to fit to that data will change. So you'll see Cauchy here, you won't see Cauchy here, okay? Because Cauchy is not bounded on that fixed bound of 0. Okay, so here, once I hit fixed bound, it's going to say, okay, here are all the distributions that at risk will try to fit to your data. This is where you start thinking about, okay, who am I presenting this data to? If it's just for me and it's my own business and I don't need to show this to anyone and I just want the best fit no matter what, I can select all of these. I can select every single one of them. If I need to communicate my results to others, I might want to remove this one because I can't even pronounce it. And people might think I don't know what I'm talking about because I can't pronounce it. Or maybe they don't know what a Pearson 5 or Pearson 6 is. I'll remove those. Okay, so this is where you let at-risk know, hey, I just want you to try these different distributions out on my data. If I click fit here, it will fit the distribution based on whichever test you choose. And you can choose the rank, you can choose to rank the results based on whichever goodness of fit test that you choose. So this one in particular is the key information criterion, which tends to favor fewer parameters. Bayesian information criterion also favors fewer parameters and is a better choice for smaller data sets. So for that person that had that question, Bayesian information criterion is going to be the test that you would want to try out because it's better on the smaller data sets. Chi-squared is typically used for discrete variables and is usually better used when there are more than 50 observations. Kolmogorov-Smirnov is more suitable for smaller samples and has a better fit for the mean versus the tail. So it'll fit tighter around this part versus this part is going to be your Kolmogorov-Smirnov. Your Anderson-Darling is going to be a better fit on the tail. So if you're modeling something that has a catastrophic situation possible, you're going to really want to fit those tails nice and tight because you want that accuracy there on those tails because the ramifications of that event happening could be so drastic. So just know that there are different tests, and if I can change between the two of them. So if I really wanted to fit amongst those tails to the right, that tail to the right, I can choose the Anderson-Darling. The gamma distribution still comes up as the best test, and if I actually go down here and mouse over these, I can actually see that the gamma distribution came in first for all of the tests except for the Kolmogorov-Smirnov. And if I go down here, the log logistic came in third for a KK test and the Bayesian, but came in first for Kolmogorov-Smirnov. So that one is going to be tighter about the mean. So then once we decide which one we want, we just click Write to Cell and we click Next. And when we click Next, it's going to say, where do you want to put this in your spreadsheet? Let's go ahead and put it with the one that came with this particular distribution. There we go. So this is the gamma distribution. And I can, again, if I want to see this, I can do round and have it round to the 0 decimal place. And it matches the other one, even though this is the Weibull distribution and this is the gamma distribution, okay? And we can see what that would look like if we go here. There we go. So you can see here that this gives us the risk gamma. And if I were to go here, this is what the risk Weibull looks like. So similar, but slightly different, okay? And it's mainly on that tail portion. So now I have this particular information here. I can actually copy this and paste it into a new workbook or a new worksheet. So maybe I paste it here and I say demand. So all of a sudden this could become part of another model, and I would still be able to use this even if this was in a different workbook. So if I did a new workbook and go back here, copy here, and put it in a new workbook here, I can close out of this one. It's not referring to it. It's actually copying out the information and representing it in its own distribution. So I don't have, you can see here, I don't have any other Excel windows open. So I can look here and say, there it is. So that's what you would do with your pre-existing data, is you would take that data and you would fit it. Also note that we have a batch fitting tool along those same lines. So we have a batch fitting tool. Let's go into our example spreadsheets and go to distribution fitting, batch fitting. And I'm going to do this one really quickly, but just to show you. So we go here, we have 4 variables. So this is historical data that you might have on 4 different variables. I can go distribution fitting, batch fit, say I want to fit these 4 distributions, and you just click fit, and it will go through and it'll say, oh, these are the best possible distributions based on whichever test you choose. So here we have our batch fit, and we can see that I accidentally selected that first column, so we can ignore this particular one because that doesn't make any sense because there's no data in it. But if we look here, we can see this first one was fit best with the triangular distribution. The second was fit best with the risk inverse Gaussian. And third is risk Weibull. Fourth is risk exponential, the exponential function. And it gives all of your mean, median, everything. It gives whether, these you can see are unbounded to infinity. If we look at the individual ones, this is a nice situation where you can actually look and see that, yeah, this fit a triangular distribution. But remember that Kolmogorov-Smirnov test, if we look here, we can see the Kolmogorov-Smirnov test, the triangular distribution ranked 10th. So if we were wanting it to be best fit about the mean, then we wouldn't want to choose triangular. We would want to look to the right and maybe choose gamma. Okay, and then if we want to choose gamma, we just go up here and there's our function for us. So how fantastic that we give all of the functions here that can then be plug and played into your other models. So that's where you want to just take a look at it and see. Okay, so hopefully that helps answer some questions. Okay, so another fitting example that I need to show you is a very popular, and it's funny because I was like, I got to remember that data set. How could I forget which one it was? It's Old Faithful. So if anyone has taken an introduction to statistics course, again, you probably have seen the Old Faithful data set. So let me just open up this. So Old Faithful data set. As mentioned at the beginning, when choosing what distribution to use, you'll want to take into account other factors such as logic, theory. In this case, visually seeing your data actually graphed out. The advantage of fitting your data in at risk is that you can see your plotted data with and in the same window with the distribution that you would like to use as an overlay on top of it. A common example of how things drastically go wrong is when you try to fit a distribution to this old faithful eruption data. In this example, we could do a batch fitting of the two variables just like we just did with the four variables. However, let's just take a look at just the waiting time. And let's first show it in the data viewer. So I'm just going to click in the data, go to data viewer, and I only want to see column C's data, so I'll change that. And I'm going to click OK. So this is our data. This is the old faithful data. Okay. So what would be the best distribution to fit this data? Well, if we're looking at this, you can see at quick glance that this is going to be interesting to fit because it's obviously bimodal. Okay, so bimodal is going to be a situation where we're probably going to want to look into some other form of fitting. So if we have this situation, if I go in and fit my data, just because I want to show you how it could go wrong if you just go, okay, let's just fit it and let's just trust whatever at-risk says and go with it. You need to make sure that it makes sense, because otherwise this is a distribution that will be presented, or maybe this is a distribution that will be used, or maybe this is a distribution. So these, you can see that if we use these examples or these distributions, it would draw from this space here to try to recreate what happened, and that wouldn't be accurate. So just know that there is a certain level of logic that you want to take into consideration. And you can see this even at quick glance. If we look at a PP chart, these lines, when this is a testing, a way to do a quick test on whether or not you have a good fit. A PP chart is, and I can do, let's do the triangle in there so the lines are a little separated apart here. You can see a PP chart, these lines should be straight if it was a good fit. A diagonal straight line is what you're looking for. That doesn't look like a diagonal straight line, so we know it's not a good fit just by looking at. So if we hadn't plotted the data and we went blindly with the suggested distribution, we might simply end up using that triangular distribution. However, after looking at the data mapped out, it would be better to work with maybe At-Risk's ARTIST tool. And for those that aren't familiar with At-Risk's ARTIST tool, let's go ahead and take a look at how we could utilize that. So before we open the ARTIST tool, let's go ahead and see what this histogram looks like just in Excel. If we go here and we say, let's do histogram, click OK. Okay, this is our histogram in Excel. That's how you would input your graph in Excel. What we want to do is we essentially want to recreate this using our ARTIST tool in At-Risk. So let's go to our At-Risk distribution here, go to distribution fitting and choose ARTIST. So we have our ARTIST tool here, and we're going to recreate the situation. And actually, I should have mentioned the minimum and maximum that showed up in our data is 43 and 96, and I can show you where I got that, but just so that I don't have to leave this dialog. Let's go ahead and say ART distribution for waiting time. We're going to do a probability distribution. We know the minimum is 43, whoops, 43, and the maximum is 96. And if we look at this chart here, there are 8 bars or 8 points that we want to take a look at. And we actually want to do a histogram because we want to recreate what's in that histogram. So we click OK, and it gives us this blank slate. All I'm going to do is I'm going to click in the center of this and will automatically give us a histogram. Now all we have to do is go in and adjust these histogram bars to match what we have here. And if I mouse over this, I'm going to see the value is 26 for this bar. The value for this is 40. The value for this is 28. So let's move this bar up to 26, or in that vicinity anyway. Let's move this bar to 40, I think it said. And let's go here to 28. And this one here is 19. 67, 69, 22. So we can go 19, 67, 69, 22, and the last one, this little tiny, tiny, tiny one here is super tiny. Just bring that down here. So this is kind of like we just basically recreated something similar. Is it exact? No, but it's okay because it's about drawing random samples anyway, but it's close to it. And this is a better distribution than a triangular distribution. So again, just like before, we're going to say right to cell, and we're going to say, let's go ahead and put that here. Click OK. It will give us this histogram distribution that now can be used as an input. Okay, so this just shows you a different way of being able to use that artist tool and have that data and be able to work around it. So basically I'm just going to go back to my PowerPoint slide here, and let's just run through other items to, or some of the industry standards some folks were asking about. Let's go here. So we have industry standards in finance. These are some of the popular ones: oil and gas, log, normal, and normal. So finance, talking Poisson, again, number of events, maybe it's crashes, earthquakes, etc. Pareto, it's severity and magnitude of events. Oil and gas, a lot of times actually in nature and in of itself, log normal is very popular. Normal for core porosity percentages. Again, this stuff is out of my standard realm, and for the person who asked about transportation, we could certainly list some theirs. Project management, triangular, and PERT. Those are two of the most popular. Triangular, typically used with when it's a new project and you're not really sure, and basically I like just mention, like, yes, I am a fan of PERT over triangular. However, if you're doing a project for the first time, it may make sense to use a triangular versus a PERT because there's no basis to give extra weight for a particular estimate, meaning there's no basis to give extra weight on whether or not it's the most likely or not, because they're all guesses at that point if it's a brand new situation. However, if you have previous data to go by, PERT may be a better option for you. Binomial and Bernoulli, it helps represent will it occur, will it not, and in that Introduction to Risk Analysis Using at-Risk webinar, that we do cover that briefly. Nature, log normal is a lot of times used in nature as well. So final thoughts: choosing the right distribution is important. It is important. However, don't panic. There is no perfect distribution, and any distribution that you use is going to be better than doing a single point estimate. Okay, so just know that don't panic. Use what's on the Common tab if you're new, and find out, do some research. Google could be your best friend as far as finding out what's popular in industry standards. Look at research papers, white papers. What distributions have they used when running Monte Carlo simulation? Take a peek at that, but also don't panic. Think about the different things. Is it bounded? Is it unbounded? Is this a situation where it would be symmetric or asymmetric, what have you? And by that, you want to use some common sense. Take a look at your data plotted out. Does it make sense to represent Old Faithful data with a triangular distribution? No, it doesn't, because it's bimodal. And there are ways to also do bimodal distributions. You can splice distributions, but we don't cover that in this particular webinar. However, feel free to look in our knowledge base. You can go to our website and under support, go to knowledge base and look up that as well. Think about who you're sharing this with. Will they understand what distribution you've chosen? And that basically wraps it up. Thank you so much for taking time to join me today. I realize it isn't always easy to carve out time to watch a webinar, especially when I go over by about 25 minutes here, but I hope it has helped you to gain confidence with defining distributions in your at-risk models. I hope you have a fantastic day. Bye for now.